there a pointer?
Yes.
And on the top. Oh, that. All right, that works.
5 minutes and 2 minutes.
Okay. All right. Hello. So I'm here on behalf of, and I think I've already gone forward, haven't I? Yes. I'm here on behalf of the MERLIN team. Scott Murchie is the PI. The team has got many folks from many different places here. It's a pleasure to be here. Phobos and Deimos are of great interest, and I suppose, technically speaking, would be a real kind of, not a union, intersection of a lot of exploration interests, since they're moons. They might be captured asteroids, and they're around Mars. So basically, everyone should love Phobos and Deimos. So MERLIN was proposed last round to the Discovery Program. It was proposed again this round. And in a nutshell, MERLIN is designed to explore the other terrestrial planet satellite system, the satellites of Mars. It's designed to take the first in situ measurements of a D-type body. The D-type is an asteroid spectral class that's been unvisited so far by spacecraft, and to close strategic knowledge gaps for human exploration of Mars's moons. To echo what I said, but a bit more seriously, Phobos in particular is really seen as a real potential. It's got great potential for human exploration on the way to Mars. So this would help a lot. So what we know about Phobos and Deimos so far is not as much as you might think, considering how many spacecraft have been in their vicinity over the decades. This is a close-up of Phobos' surface. This is a close-up of Deimos' surface. Here are the two of them in whole. Their surfaces and densities indicate that they have had some different evolution. For a long time, it was assumed that they were twins of one another. That might not actually be true. We see that Phobos' surface is much more heavily cratered. It has these grooves, which are in a lot of ways sort of signature features of Phobos' surface. There have been several different theories about how they formed. Its density is a little under 2 grams per cubic centimeter. Deimos, on the other hand, is much more lightly cratered, and it's much smoother surface. It looks like it's mantled by dust. Its density is quite a bit lower at about 1.5 grams per cubic centimeter. Phobos' surface is dominated by this big crater called Stickney, and there's a spectral unit on Phobos' surface which is associated with the rim of Stickney. I guess I'll show you guys here too, since you've been so patient on that side of the room. And it's somewhat bluer than the rest of Phobos. The background part of Phobos and Deimos both have very similar spectra and are much redder than this part of Stickney, or this part of Stickney's rim. So understanding what's causing these differences and what's causing the morphology in the first place, and what's causing this color differences, is going to give us a lot of information about small bodies in general. So Phobos and Deimos spectrally resemble outer solar system bodies, which is part of what makes them really interesting. Here on the right, we have kind of a bit of the zoo of asteroid spectra. Down here with a relatively flat spectrum is Matilda, C-type spectrum. These guys here with olivine and pyroxene bands are Eros and Itokawa, and these really red spectra are those of Phobos, Deimos, and then this other unit on Phobos, the bluer unit, which you can see is only blue relative to the red parts. And they're similar to outer belt and outer solar system bodies like these Trojan asteroids, which co-orbit along with Jupiter. Comet Siding Spring also has a similar spectrum. So these are associated with very primitive, organic-rich bodies. So that led to the obvious conclusion that, okay, Phobos and Deimos are probably captured primitive bodies. However, dynamically, it's very, very difficult to capture Phobos and Deimos. So dynamicists don't tend to favor capture for that reason. Some other possibilities that have been brought up are maybe there was a giant impact on Mars. I think we might hear more about that at some point tomorrow. Maybe does Robin Canup talks about that tomorrow, I think. It's also possible that maybe stuff co-accreted in that part of the solar system and was space weathered to be very red. So again, all of these have very different implications, not only for Phobos and Deimos themselves, but for conditions early in solar system history. If it could be shown, for instance, that Phobos and Deimos are pieces of Mars from very early on, then obviously the Mars community would be particularly interested in finding out what they're like. So there are a set of science questions associated with MERLIN that were developed for this proposal, but they're also pretty general for Phobos and Deimos science in general. What are their compositions and what are their origins? Are they actually rich in carbon and volatiles, like we might suspect from their spectrum? What geological processes affect their surfaces? What's causing these grooves? What are the moon's interior structures, and why are their densities as different as they are? And then again, from an exploration point of view, the measurements that MERLIN will make should close strategic knowledge gaps relevant to in situ resource utilization. Are there hydrated minerals? Is there something to get at on the surface? Regolith mechanical properties and the like. So MERLIN will do multiple flybys of Deimos, and then will rendezvous and then land on Phobos, potentially on both the blue and the red unit. Everyone loves the decadal survey. I'm not going to go through this except to point out that all these colors are associated with instruments on MERLIN, and the MERLIN science questions and the kinds of questions that are in the decadal survey about planetary science in general are addressed often through multiple instruments by MERLIN. Okay, so I'm going to really date myself here. Much like a McDLT, which used to have a hot side and a cold side, for those of you who remember McDLTs, MERLIN has a landed side and an orbital side. The orbital instruments are kind of all on one face. This includes the imaging system. It includes a radiation monitor, which I guess is not visible, which would suggest it's not on this side, but that's me. There's a dust particle counter, and then there's the deep space optical communication, which is a optional instrument that NASA was encouraging people to fly. The landed side has a different set of instruments. There's an arm, I guess, which has on it a turret with an APXS, an alpha proton X-ray spectrometer, and a microscopic imaging spectrometer. And then there's a mini gamma ray spectrometer on the forearm, so we get a lot of elemental measurements from the surface. And then there's a landed stereo camera which operates on the surface. The mission profile, when Earth is here upon launch, Mars is here upon orbit insertion. Launch is baseline for November 2021 on a low performance. I think this is the lowest performance end, and that was 5401. And then it rendezvous, Mars orbit insertion is January 2024, so kind of a typical time frame there. Early on in the mission, then there are a set of very elliptical orbits which are used in the process of circularizing things, but also it allows encounters with Deimos at different lighting conditions, and it allows sampling of the dust belts associated with Phobos and Deimos that have been hypothesized to be there for some time, but have never been directly actually sensed. As noted here, the dust counter measures those dust belts. So this is the early phase. Then we have Phobos Rendezvous. So this is a view, if you're standing on Mars, if you're on the Mars-Phobos line, and Phobos would be in the middle here, this is the track that MERLIN takes around. So they're non-Keplerian orbits around Phobos. They are Keplerian around Mars, but they, as you can see, allow measurement of Phobos and measurements of all parts of Phobos from a range of illuminations over a course of a few months that allows global stereo and color imaging. So a really great data set for Phobos. This shows kind of the kind of data we might expect. Here up at the top is 1 meter per pixel from Eros. So this is the kind of resolution you would have for Phobos as a whole, and the kind of stereo imaging resolution we could expect from MERLIN. Down here is 8 meters per pixel, so comparable to what HiRISE gets. This is a HiRISE image, but instead of just one color, This is 11 colors. So again, a really spectacular data set for understanding Phobos and small bodies in more general. Once the global characterization of Phobos is finished, there are then a set of low altitude flyovers providing very high resolution, 5 centimeter per pixel imagery over the surface, and 40 centimeter per pixel color stereo that allows potential landing sites to be characterized, and we can understand, from both a safety and a science point of view, which landing site we prefer. And then finally, in October 2024, MERLIN would navigate to a landing in a pretty tightly precise area. So once you're on the surface, and that'd be Mars back there, MERLIN would contact the surface with its arm. There is a particular direction that we would want Phobos to land, that we want MERLIN to land, so that the solar panels can get maximum sun, and so that we would have morning sun on the area where the arm is, to allow measurements to be taken in the morning and then analyzed over the course of the day, so you're ready for the next morning's observations. So the elemental observations elemental measurements are made with a couple of instruments. A gamma ray spectrometer. This allows major elements and carbon to be measured to some tens of centimeters depth. This does not have to be deployed. It distinguishes between major compositional types. So here, for instance, is iron versus oxygen and iron versus silicon, and the major meteorite types all separate out pretty easily. And certainly a Martian versus a asteroidal composition is very easily distinguishable. They also allow indirect measurements of hydrogen to hundreds of parts per million. Patrick Poposky demonstrated this with the NEAR gamma ray data set just earlier this year. The APXS gets a different set of elements. This is measured just in the top tens of microns, so it allows kind of a very surface versus more bulk measurement of elements. And again, it discriminates among analogs that are maybe more similar to each other than these broad categories from the gamma ray spectrometer. And then comparison of some of the more volatile elements allows us to understand space weathering better if some elements are absent from the very surface but present in the gamma ray spectrometer measurements. And then finally, the imaging spectrometer works like this is like the spectrum that Barb showed over visible and near IR wavelengths, allows minerals like olivine, pyroxene, clay minerals to be distinguished from one another, and has very high spatial resolution, allowing individual grains to be measured. And so in summary, MERLIN, which again, hopefully we'll get to fly soon. It's in the current discovery round, so hopefully we'll get some good results. This will be the first dedicated small body lander that the US has flown. This will be the first in situ exploration of Mars's moons, the first mission to a D-type body, and it would close strategic knowledge gaps for human exploration of the Mars system. And that's what we have. Thank you.
Thanks very much. We've got time for maybe one or two questions.
I'm K.R.S. Murthy. A good presentation. You talked about neutron radiation and alpha radiation in different contexts. Depending on the electronics that you use on board, if it's below 28 nanometer node semiconductor, then it's susceptible to alpha radiation and neutron radiation. On the Earth, it is noticed, and I don't know what kind of a node you use in the semiconductors, not that you may be familiar. It creates what's called a soft error. Have you thought about it, understood it, and so on?
I'm going to have to punt that question. I personally, I'm on the science team. I guess I would best say that the team is very experienced in a lot of missions.
I understand that.
And I
Don't worry.
do not know the literal answer to
We'll
your
talk
question.
offline. There's a problem that we face on the Earth itself, with packaging having alpha radiation and neutral radiation coming from the space, affecting the soft error, which is not a stuck-cut fault as it's called. You cannot know where and when it happens. Soft
the, I think Mars has a few unique things that make it easier to capture a moon like Phobos into its orbit. One addition to that is Mars has most of the oval craters in the solar system on a planet, which this indicates that it's probably captured many Phobos-type asteroids in the past. The only time you get an oval crater is when you come in at a very slow, at a nearly parallel. So I'll say, and also this Stickney crater could have made the difference in density between. It could have driven off enough of the volatiles to make it so that's the difference between Deimos in the density and Phobos. I'd like it'd take more time than I think I should take to describe how I think that the capture is done. But it's as hard to put stuff into orbit from an impact than from a capture.
Sure. Just to take just a couple of seconds, my impression is that part of the issue with capture is that both Phobos and Deimos are in equatorial orbits, and both are evolving in directions that make it difficult to see how you'd have to capture them in an order that seems difficult. I'll also note in terms of Stickney that Deimos has a crater that's even bigger than Stickney relative to its size. So it's clearly an open question that hopefully we'll be able to answer. But thank you.
Thanks so much.